Hello everyone, welcome to my calculus lecture. In this lecture, we study derivatives of logarithmic and also exponential functions. So we study first derivatives of logarithmic functions and then derivatives of exponential functions. And we are going to also talk about uh, uh, the logarithmic differentiation as well. So in this order. Okay, first, I'd like to talk about the number e. The number e is a very famous number. It appears uh, a lot in many natural phenomena. Mathematically, this number is defined by the limit. This is not the only way we can define the number e, but one way we can define it is, as the limit of this function here, 1 plus t to the power 1 over t. When t goes to 0, this limit does exist, and that value, the limit, is going to be denoted by number e. Its numerical value goes like yeah, 2.71, 8281, 8284, 590, and so on and so forth. So this is as much as as far as I could go. I remember. Okay, but normally like the 2.718 numerical calculations. So going back to lecture slide. Okay, so using this definition of the number e, we can find the derivative of the logarithmic function. Okay, y equals ln of x. So it turns out that the derivative of ln of x is given by 1 over x. So how do we know? To see that, let's go back to my notepad. So we want to show d by dx ln of x equals 1 over x. Okay, so by definition, this would be limit h goes to 0 ln of x plus h minus ln of x all over h, right? Now using properties of well-known properties of logarithms, the top part, the numerator can be written as ln x plus h over x, and then we have what? This over h, right? So denominator can be moved to 1 over h here, right? And now you know that this is same as ln of 1 plus h over x, right? Okay. Now what I'm going to do is multiply 1 over x by 1 over h by x, and then divide by x. Same thing, right? Give and take. So you know, still like we retain this equality. So 1 over x, that has nothing to do with the limit, so I can put that outside of limit. X over h ln 1 plus h over x. Okay, now again, you know, this is a well-known property of a logarithm, right? We can move this number in front of log as the exponent of this 1 plus h over x. Okay, so that's gonna be ln 1 plus h over x to the power x over h. Okay, now what I'm gonna do is the following. So here I'm going to set you know, the h over x. So h over x, set it by another variable t. Okay, so let's set. Then what's going to happen is, in terms of this new variable t, when h goes to 0, obviously t goes to 0, right? Clearly you can see that. So limit t goes to 0. And we have ln 1 plus t to the power. Note that, you know, h over x here, x over h, so that these two are like what? The reciprocal of each other, right? So this will be 1 over t. Okay, now if you also remember log function, you know, the ln is what? A continuous function, okay? Continuous wherever it is defined. So, you know, that, in that case, what is that? This limit can go inside of the continuous function, right? It's the property we learned, right? About continuous functions, okay? So limit goes inside. Good. Now what do we have? So this is going to be 1 over x. The inside bracket, this limit is e. Okay, that's e. That's going to be the number e. So we have ln of e, which is 1. Okay, so this equals 1. So at the end, we have 1 over x. So this completes the proof, right? So we just showed that, or we derived, you know, this formula here, right? So derivative of ln of x equals 1 over x. Okay. All right. So let's get back to my lecture slide. All right. And now, what is that? What about, like, you know, so this is like a special type of log function, right? ln of x. That's the case when, you know, the base of logarithm is e, right? But what about, you know, any like general like the logarithmic function, like the base is other than like e. So what are we gonna do? Here's the thing: we can always use the change of base formula. For instance, log with base a of x, right, can be written as ln x over ln a. Then we can find the derivative of this log base a, log with base a of x, right, is given by the derivative of this guy here, right? And we already know that the derivative of ln of x is 1 over x, so we end up getting 1 over x times ln a, right? So that's the derivative. Easy, right? Okay, now we are moving to derivatives of exponential functions. Okay, now we need to first record that the exponential function y equals e to the x is the inverse function of y equals ln x. So, if you define, so there are two ways you can do this. You can define exponential function first, and then you can define the log function ln x as its inverse function, or vice versa. You can first define log function ln x, and then you can define e to the x as its inverse function. Okay, so they are sort of like inseparable. Okay, right. So, so what that means is that they satisfy the following relationship. Okay, so y equals e to the x if and only if x equals ln y. So what happens is that how do you, if you remember, right? So how do we find the inverse function? First, the thing is that you swap x and y. Why are we doing that? Because given function and its inverse function, they swap, right? They swap the domain and the range, right? That's why we swap x and y. So if you swap it, x equals e to the y, right? We have it x equals e to the y. And then next step is you solve that for y, okay? You solve that for y. However, I mean, we don't know, how to solve it, because we know that y exists as an inverse function, because the exponential function is a one-to-one function, if you remember. So it always has the inverse function. However, we don't know how to solve x equals e to the y for y. So people decided, well, in that case, let's assume that you solved the x equals e to the y for y, but that is denoted by ln of y. So x equals ln of y. Okay, so that's what happened. So because of that relationship, right, they always satisfy this. Okay, so using this, actually, we can find the derivative of e to the x. And it turns out that the derivative of e to the x is very interesting itself. No matter how many times you take the derivative of e to the x, it always the same. You get the same thing as e to the x. Okay, so let's see how actually we can use this relationship, right? Basically inverse relationship to get this one. So for that, we are going to get back to my notepad. So again, we have so y equals e to the x means if and only if, so that's a logical symbol, right? For if and only if x equals ln of y. Okay, so starting from this y equals e to the x, that means it is equivalent to saying x equals ln of y. So we take the derivative of this with respect to 1, okay? So differentiate differentiating this guy x equals ln of y with respect to 1, x, the variable x, we get left hand side is x, right hand side ln of y. Remember, implicit differentiation that has to be used, right? Because y is implicitly it is a function of x. So first it's 1 over y, and then you have to multiply that by y prime. Implicit differentiation is what? Nothing other than the chain rule, remember? Okay, so here we get the following thing, y prime equals y, but then what was y? Well, what is y? Y equals e to the x. So we just showed that, we just derived that uh, derivative of e to the x with respect to x, that's e to the x. Okay, then yeah, how about the more general cases? So the base of exponential function is something other than like e. So in general, like what if we have y equals a to the x? What do we do? Same relationship, the holds, right? In that case, y equals a to the x means x equals log with base a of x. Okay, that's what we have. Oh, I'm sorry. It's not x, it's y. Okay, so we do the same thing. You take the derivative, so with respect to x, so left hand side is 1, right hand side is going to be, we just talked about derivative of this guy here, right? That's going to be 1 over y times ln a, and then you have to multiply that by y prime. So this implies that y prime equals y times ln a. So y equals e to the x. So e to the x times ln of a. Okay, so that's the derivative. So we just found out that derivative of a to the x equals e to the x times ln a. Okay, ln of a. So as you might have noticed, in this case, I didn't use the fact that the derivative of e to the x is just e to the x, totally like separate from this, I was able to get, the derivative of a to the x, right? Okay. And in fact, the previous formula, e to the x, derivative of e to the x equals itself, can be actually obtained, as a special case of this formula here. All right, because if you choose the special cases, so if right, so if a equals e, right, then from this formula, the dx e to the x equals e to the x times ln of e, but knowing that ln of e equals 1, we get e to the x. Okay, so totally like independently from this derivative of e to the x, we can actually find all of them, right? Okay, including when a equals e. How about that? Can we actually use this, right? Yes, we can. Another way you can show is so uh, this one here. Note that, so you have, so from here, right, a to the x, that equals, again, using well-known, the formula or actually identity from, the algebra, right? So it can be written as a to the x can be written as e to the x times ln a. Okay, x times ln a. So you take the derivative of this, so d by dx, a to the x, that's same as d by dx e to the x times ln a. So the e to the x times ln a is a composite function, right? A composite function. So that's going to be using this formula. First, it becomes itself, right? X e to the x ln a, and then you have to multiply this by the derivative of x times ln a, which is just, ln a is actually constant, so that's going to be, what is that? ln a, right? This part here. And then e to the x times ln a is nothing other than a to the x, so a to the x. That's exactly the same as what we just showed here, right? Okay. Uh, yeah, right here. Okay, the same thing. So you can do it that way also. So first, they calculate the derivative of e to the x, and then using that, you can also find the derivative of more general, like a to the x. All right. So let's get back to my lecture slide. Okay, so we just talked about derivative of a to the x, right? Okay, and same thing, I already talked about all these, right? Oops. Okay, I covered all those. Right. So next one, as an application, we can also prove the power rule. But of course, we did that earlier. But the what is that? That's a special case when n, the power exponent n is the positive integer case. Right? We proved it. But in fact, as I explained at that time, even when n is an arbitrary real number, still like the power rule holds, right? So this time, like, let us consider x to the power n. Again, the power function, the x to the power n, where x is positive and n is any real number. Okay. Now, so using the formula in this case, x to the power n, it's the same type of formula we just did, right? This can be written as e to the n times ln of x. Okay, so using the property, well-known property of properties of exponents, right? Along with the chain rule, we can show that the derivative of x to the power n equals n times x to the n minus 1. Okay, so let's see that. So I'm going to move to the next page. Okay, so here again, x to the power n can be written as e to the n times ln of x, right? So the derivative of x to the power n That's same as the derivative of e to the x ln x. So, using the chain rule, this is going to be e to the x ln x times derivative of x ln x. Okay, so here x times ln x, you will have to use the product rule, right? Okay, so using the product rule, you are going to get 1. So, when you take the derivative of x, that's going to be 1. So that's going to leave ln x plus x times the derivative of ln x is 1 over x. So x cancels out, leaving only 1. And then e to the x times ln x. Oh, sorry. I think something is wrong, right? Something is not right. Yeah, I was doing totally something different. Okay, that was weird. Pardon me. Okay, it was n. So actually n times ln x. So it's going to be e to the n times ln x, and then multiply that by derivative of n times ln x, right? ln x. Okay, so derivative of n times ln x is just n over x, right? So n over x, because n is a constant. And then we have e to the n times ln x. Okay, e to the n times ln x is nothing other than x to the power n. So we have n over x times x to the power n, which equals n times x to the n minus 1. So this completes the proof. Okay, so here, like what, there is no restriction. There is no restriction required on the exponents n, right? That it has to be positive integer or anything. It could be any number, right? Any real number. So it works. Okay. Oh, went too far. What's going on? What's going on? Okay, so next thing I want to talk about, let's see, yes, with the power rule. So next thing, last thing we want to talk about is logarithmic differentiation, right, as an application. So what is logarithmic differentiation? Often we stumble onto like functions involving product, quotient, and powers. They're pretty complicated. Okay, the functions, and so using logarithm. Okay, using by taking logarithm, what we can do is we can actually split, not split. We can actually break that complex function into the smaller pieces. Okay, and then so I mean we do that first before we take the derivative. So that actually process makes the whole differentiation much easier in many cases and also quicker, okay, to calculate. So that's the idea of a logarithmic differentiation, and I'm going to show you how it does work using a couple of examples. Yeah, so I just mentioned here, right? The same thing. So this allows us to break a complicated function into simpler pieces using properties of the logarithm before we differentiate it. So that's what pretty much what I said, okay, earlier. And so this whole process, there's typo. This whole process is called logarithmic differentiation. Okay, so here are the examples. Using logarithmic differentiation to find the derivative of this function here, okay? This function looks pretty complicated. So let's let's go to my notepad to calculate that. All right. So example. So the function here we have is y equals x times square root of x squared plus 1 over x plus 1 to the power 2/3. 2/3, right? That's what we have. Let me check. I just want to make sure that I got the right thing, okay? Yeah, looks like it. Okay, so here's first step. So we take the logarithm first. Take a natural logarithm each side. So that's going to be ln of x times square root of x squared plus 1 over x plus 1 to the power 2/3. Now, using properties of logarithm, this can be separated to ln x plus ln square root of x squared plus 1, right? But square root is same as what? X squared plus 1 to the power 1/2, and that power can be moved in front of logarithm. So it's same as 1/2 ln of x squared plus 1, and then minus ln of x plus 1 to the power 2/3, but this power also can be moved in front of logarithm. So we get that. Okay, now we are going to take the derivative. So differentiating left-hand side using implicit differentiation, we have 1 over y times y prime. Right-hand side, so derivative of ln of x is what? 1 over x plus 1/2 times derivative of this is what? 1 over x squared plus 1, and then multiply that by derivative of x squared, which is 2x, minus 2/3. This is going to be just 1 over x plus 1. So this equals 1 over x plus 2 cancels out. We have x over x squared plus 1 minus 2 over 3 times x plus 1. So finally, remember what we are trying to find is y prime. So you just need to solve this for y prime. So y prime is going to be, or dy by dx, right? That's going to be this whole thing multiplied by the function y. And what is y? Why is this function here? So the final answer in this case is going to be x times square root of x squared plus 1 over x plus 1 to the power 2/3. Okay, and then multiply by 1 over x plus x over x squared plus 1 minus 2 over 3 times x plus 1. Okay, so it's not bad at all, right? It's not bad at all. But just imagine, you don't have to use this logarithmic differentiation. You could have used the what? You could have used the, the product rule, quotient rule, and the chain rule to find the derivative of this. You are more than welcome to try it, but it's going to be really messy work, right? Pretty complicated business. But this is much simpler and quicker. So the whole process which it just did, that's called a logarithmic differentiation. Next example is find the derivative of y equals x to the power x, where x is positive. So that's a weird function, right? Okay, if you might be hasty to apply, in this case, what's the big deal, right? We have power law. No, you can't use the power law. Power law works when the exponent is just number, fixed number, but in this case, it is not a number. It is another function, another variable. So again, I'm repeating that. You can't use the power law here, right? Okay, so this is some weird function, but no problem. So next example we want to talk about, right? So we have this weird function, y equals x to the power x, okay? Where x is positive, okay? All right, so there are actually two ways you can do, okay? We can use it logarithmic differentiation, okay? So we do exactly the same thing. So take the natural logarithm. So that's going to be x times ln of x. And then you differentiate this the equation. So left hand side is going to be y prime over y. Right hand side, by product rule, we have 1. So the ln of x, derivative of x is 1. So ln x plus x times the derivative of ln x is 1 over x. So x cancels out, we have 1. Okay, so this implies that y prime equals y, which is x to the power x times ln x plus 1. Okay, so that's the derivative of x to the power x, right? You don't actually, in this case, you don't also, you don't have to use the implicit differentiation. So this is second method, right? I would like to talk about. So you can actually write down, the note that x to the power x can be written as e to the, again using the properties of exponent, e to the x times ln x, right? That's the one actually I mistakenly wrote earlier, right? But that's the same thing as x to the power x. Okay, so the derivative of e to the, x to the power x, that equals the derivative of e to the x times ln x. So using the chain rule in this case, because this is a composite function, e to the x times ln x times derivative of x times ln x prime, right? And that's e to the x times ln x is nothing other than x to the power x. And then this one here, we just actually calculated earlier, right? Using product rule, we get 1 plus ln of x, right? 1 plus ln of x. So either way, in this case, I mean, this is not bad at all, okay? So either method is just fine. Okay, folks, more details of my discussion here in this lecture note can be found in my, the lecture note at the following address. Okay, so as usual, this address is hyperlinked. So all you have to do is just click on it to get to the lecture note. And also, if you want to see visit my main, blogger site, just click on this word, the blogger, right? It is also hyperlinked, so it will take you the main blogger site where you can find many other lecture notes as well. Okay, so thank you for watching and listening to my lecture today. You have a great day. Bye-bye.